Hello, finally got some new content for you guys. This is my creative component for my master's degree, and it's on the idea behind the Birch and Swinnerton-Dyer Conjecture. So just trying to explain the meaning by what's being discussed here, and it's roughly that the analytic rank is equal to the algebraic rank for elliptic curves. So as a three-part series, let's talk about the elliptic curves basics. So here's the elliptic curve. The equation, it's a cubic equation, so it's a cubic polynomial. Just keep that in mind. And the variables and the coefficients, they all come from a field, K. It's any field. For instance, the rational numbers, that's a field. The integers is not a field. The real numbers are a field. The complex numbers are a field. Z mod PZ, that's a field. So that's how we define the elliptic curve. And we impose this restriction that the discriminant, -16 times stuff, is non-zero. And that's going to make sure that our elliptic curve is non-singular. So our elliptic curve won't have any cusps or nodes, like self-intersections and things like that. So it'll be smooth. Alright, and incredible fact about elliptic curves is that they form a group. All the points in the elliptic curve, when you put them together, forms a group, an algebraic group. And what you need to do, though, is you need to add this point at infinity, and we denote that by a script O. And that turns out to be the identity of our group. So if we add that point, we get a group. So when we use this notation a lot, E of K. So when we talk about the elliptic curve, we're really talking about all the points that satisfy this cubic polynomial along with our extra point at infinity. So that's going on like kind of, that's what we mean by E of R. In this case, E of R, that's the elliptic curve with real coordinates. So x and y are real coordinates, and the coefficient's real. So this is what it looks like when you graph it in the xy plane. It looks like this. Here's an example. And when you tinker around with the coefficients, you get different shapes. So here's a possible shape. Here's yet another kind of possible shape. And so these all three that I've shown you have one component. Here's an example with two components. It's got this kind of egg shape here, but it's not connected to this bit here. It kind of looks parabolic in some ways. So that's an idea of what it looks like when we graph the elliptic curve. So if we're going to talk about a group, we need to define how the group works. We need to define how the group law works, how the binary operation works. In other words, how to combine 2 points in the group. So the way it works is we take any 2 points and geometrically we just connect them with a secant line. And there will always be a third point of intersection. And so what we do with that third point of intersection is we reflect it over the x-axis. And that'll be our result. So it seems kind of strange, but that's what we do. And so that's how the group law works. And it's an abelian group. The reason why it's abelian just stems from the fact that if I think of P1 plus P2 is the same as P2 plus P3, because I'm still connecting the two with a secant line, and the result will still be the same. The third collinear point is still going to be the same. So when I reflect it over the x-axis, it's still the same. So that's how the group law works out geometrically. And so we talked about how any line here, it's always, so what we're going to need is if we add 2 points, we always need a third point of intersection if we're going to have this defined binary operation. So we define that third point of intersection reflected over the x-axis to be the sum of the 2 points. So if we're gonna, so we're always going to need to have that third point on the line, aren't we? If we're going to make this a group. So turns out that there always is a third point of intersection, and it comes down to the complex conjugate root theorem. So if you remember when we defined the elliptic curve, it was a cubic polynomial, and cubic polynomials have three roots, three complex roots at least, and at least one real root, possibly three. You can't have two real roots and one non-real root for a cubic polynomial. That's a combination we can't have. And that comes down to the complex conjugate root theorem. So if we have a complex root, then its conjugate is also a root. So that's why we can't have two real roots and one complex root, because if we have a complex root, we would need an actual additional. We would actually need an additional complex root, and that would be four solutions to a cubic polynomial, which can't happen. There are only three solutions to a cubic polynomial. So that's why any non-vertical line, if it has 2 points of intersection in real coordinates, it's going to have 3 points. So that's just a little detail why the group law makes sense. Geometric group law makes sense. And so what we do for vertical lines is we add that point at infinity. That's where that's going to come in. Because if you look at right here, if we make a vertical line, it's not going to intersect the curve at a third point. So that's where the point at infinity comes in. And we'll talk about that in a minute. So let's look at geometrically about how the case works when we want to add a point to itself. What happens if we want to add a point to itself? So we're not connecting 2 points with a secant line. In this case, we're drawing the tangent line on the elliptic curve at that point. So the reason why you can make sense of this by thinking of a tangent line as a limit of secant lines, as the points on the secant line get closer and closer to each other. So that's how we work with adding points to itself. We make the tangent line that always have a third point of intersection by the reason we just discussed, and then we, just like before, we reflect that over the x-axis to get our third point as a result. So that's how that works. And this slide is titled Double Intersection. So it's worth noting here that P1 is you can think of it as a solution of order 2 to the intersection between the elliptic curve and this tangent line here. So if it were a solution of order 1, it would just pass straight through it. But it doesn't. It grazes the surface and it goes along the top. And we've seen things like that, like y equals x squared, how x squared, the graph just goes down and touches the x-axis but goes back up. That's because 0 is a solution to that polynomial of order 2. It's a 0 of order 2. Alright, here's how the vertical line case, here's where that point at infinity comes in. So what happens if we want to add a point to another point? When we connect the secant line, we don't get a third point of intersection. This is where the point at infinity comes in that we add. So if you're familiar with projective geometry, the idea behind projective geometry is that all parallel lines must intersect. That's the kind of the fundamental axiom for projective geometry. So parallel lines must intersect. And in our case, we're concerned about the vertical lines. So we add this point at infinity, and that's going to be the intersection of all the vertical lines. And this sort of compactifies the curve. And you may not be familiar with the idea behind the notion of compactness. It's a topological idea or advanced calculus idea. So we won't go into that too much. Basically, this is how it works. When you have a vertical line, when you connect the two, you don't have a third point of intersection, but you actually do, because we define that point at infinity to be that sum. And that is our identity, the point at infinity. Here's an interesting situation. What if you draw a tangent line to a point, but you don't have any other points of intersection? the tangent line only crosses through the elliptic curve at one point. So we're familiar with situations like this, but we don't realize it. If you think of the graph y equals x cubed, the graph y equals x cubed, it has a root of order 3 at 0. And that's the exact same thing that's happening here. This point 0, 1 is a solution to the intersection between the curve and the tangent line. It's a solution of order 3 to the intersection. So in this case, we think of the third collinear point as being itself. So if we want to add this point to itself, its third collinear point on the tangent line is itself. And so as normal, we reflect that over the x-axis, and that's the result. So that's how it works for a triple intersection. That's kind of cool. So it seems kind of strange why we reflect it over the x-axis. Why do we do that? So we can talk about what goes wrong when you don't reflect it. So here's what goes wrong. If you just take P and Q to be just any points on your elliptic curve, and then you make the secant line connecting them, and then that third point to be the result without reflecting it, well, then P plus R is also going to be Q, because P and R are on the same line, and we know that Q is also on that same line. So P plus Q is R, P plus R is Q. Let me go back here for a second so you can see kind of, here we go. So like imagine this is your P, this is your Q, and this is your R. So if we don't reflect, if we just define P plus Q to be R without reflecting it, then P plus R must equal Q. Right? So what happened? Why is that a problem? Well, if we add these two equations together, we have 2P over here on the left. We have a Q and an R on the left, and a Q and an R on the right. So those are going to cancel out and just leave our identity. And so what does that mean? That means in general, every point is order 2. Every point, when you add it to itself, you get the identity. And why is that a problem? Because, for instance, if you take this point here and you add it to itself, so the result is going to be the third collinear point, which is right here. P plus P is S. But that's not the identity, is it? It's a point on the elliptic curve. It's not the point at infinity. So that's why we need to reflect, because if we don't, this stuff happens. So here's the algebraic group law. We're not going to talk very much about this. It's boring. But you define the identity as normal. That's how it works in every group. If you take a point and you add the identity, you get the original point. And for elliptic curves, if we take a xy coordinate and add it to another xy coordinate, but the y coordinate's negative. So in other words, when you connect these two, you get a vertical line, then the result is infinity. So you can think of this stuff here, this is how I think of it, is I can think of these four kind of things as making the geometric group law work out algebraically. So we're going to move on from there though. So what we're interested in our talk here is about the Birch and Swinnerton-Dyer, which concerns the elliptic curve over the rationals. So the field that we're talking about is not the real numbers, but it's the rational numbers that we're really interested in. And there's a theorem by Mordell in 1922. So as you can see right off the bat, people have been thinking about elliptic curves for a very long time. And he came up with a result that was, I think it's like 150 pages, the proof or something like that. It's extremely complicated. But the result is extremely simple and extremely useful. That every elliptic curve with rational coordinates is finitely generated. So this group is finitely generated. What does it mean for a group to be finitely generated? That means there's a finite set such that every element in the group can be written as a combination of those elements alone. some integer combination of those elements, some finite sum. So that's what it means for it to be finitely generated. Let's recall something else before we talk about this theorem. What is a torsion subgroup? So this is another modern algebra concept. And so basically the idea is that you take all the finite elements in the group and you put them together and it forms a subgroup. Take all the finite elements, all the elements of finite order. So all the elements that when you add the element to itself enough times, you eventually get back to the identity. Remember, that's not always the case, but if it's a finite order, then it will always happen. So if you take all the elements of finite order, you put them all together in one set, it makes a group. We call it the torsion subgroup. And theorem by Barry-Mazur in 1976 says that the torsion subgroup always looks like one of these two things. It's an extremely restrictive idea on the torsion subgroup. So all the finite elements, all the finite group looks like one of these two pieces. So I think there are 16 possibilities in total. So for instance, the torsion subgroup can be cyclic up to order 12 but not 11, and it can look like a direct product of even powers of integers here. Alright, so just to be explicit about what we're talking about, the torsion subgroup in general is defined up here, but when we're talking about the torsion subgroup for our case, the elliptic curve, it's the finite points on the elliptic curve, which is the points on the elliptic curve that when you add them to itself enough times you get the identity. Doesn't always happen, but if it does, then it's in the torsion subgroup. So you combine these two theorems that we just learned, the fact that the presentation for the torsion subgroup and the fact that every curve is finitely generated. And so if we have a finitely generated abelian group that always has one of these two torsion subgroups, we can present the form of the group. We can present what it's isomorphic to, what it looks like, how to think of it. So we think of this group, this elliptic curve, this extremely complicated object, this cubic polynomial and all the solutions on it. We can think of it as just the right hand side here. Some power of the integers as a direct product of some torsion piece here. And R is what we call the algebraic rank. So what's the right way to think about this? So you can think about it like it's the number of powers of integers. So it's the number of integer dimensions that the points on the elliptic curve with rational coordinates sort of spans. So it's kind of a measure of how big this elliptic curve is, how infinite it is, how many infinite dimensions there are, integral dimensions. And notice here that there's nothing on this slide about saying the possibilities for R. It's not restricting R to be less than something, it's not saying that it can be anything. The reason for that is that we don't know. It's unproven what the possibilities are for R. We've narrowed down the torsion piece to this very small number of possibilities, 16 possibilities for the torsion piece. For the infinite piece, we don't know. We don't know how many possibilities there are. Most people, well, I shouldn't say most people. I'll say, how about this? Some people believe that it can be arbitrarily large. In other words, that there can be 100 integer dimensions for this elliptic curve, 1,000, 1,000,000, so forth. But so far, all that's been proven is that there exists an elliptic curve that's at least rank 28. So that's the biggest curve that's been shown to be true, shown to exist. And Noam Elkies, mathematician Noam Elkies, was the world record holder for showing what the highest rank possible is. And how did he prove it? He proved it by giving a curve, and it looks like this is the equation for it, and showing that there are 28 independent points, and all generate their own integer dimensions disjoint from the other ones, except the trivial intersection, of course. So he presented. So this is how you do it. If you want to show that there's a rank, there's a curve, there exists a curve of rank greater than 28, like say 29, you're going to have to give a curve, and you're going to have to provide points on that curve and show that they're all independent. So for dramatic effect, I didn't reformat this. So actually, this equation, it goes on for another 20 digits. And for dramatic effect, and because I'm lazy, I left it like this to show that the curves, when you get to a high rank, they become very complicated, really hard, really big numbers to deal with. And of course, computers have trouble when the numbers get really big. So this is a good time to talk about the generalized Weierstrass equation. So this form, notice that this form is a little bit different than what we talked about earlier. In the form that I discussed on slide 1, we just said y squared equals x cubed plus ax plus b. So what is this xy, y, and negative x squared term here? So it turns out that you can reduce this equation right here. You can reduce it to the form that we talked about earlier, the y squared equals x cubed plus ax plus b, by doing a change of variables, a bunch of change of variables. It's very complicated. And in order to do that, so that'll eliminate these three terms here, so you can present a simpler version of your curve. But in order to do that, it should be mentioned that you have to divide by 2 and you have to divide by 3. That's part of the process of the change of variables. So as long as you're working over a field that has characteristic that's not 2 and it's not 3, then you're fine, you can do that. So that's that. This gives you an idea of when most of the progress was made. So it appears that steady progress was made throughout the 70s, 80s, and 90s on presenting the curves of high rank. But after Elke's in 2006, no new progress has been made. So this makes sense that there was a lot of progress during this time because they started using computers. Like in the 70s, 80s, computers became accessible and things like that for mathematicians. So that's what that. But at some point we just kind of got stuck. The numbers get so big, so hard to deal with, that it's just too hard. Alright, so that's it for part 1, and I'm going to release some more videos soon, but that's all we got on the algebraic side. We finished today, and I hope you'll check out the rest of the presentation. Thanks for watching.